Hey, hi everyone. In this video, we are going to solve the Leetcode problem of the day, and the problem is sum of all subset XOR totals. In this problem, we are given an array, something like this, and we need to output the sum of all the subset XOR totals. So what it means is you need to find out what are all the subsets which are possible for this particular array. For example, if the array is 5, 1 and 6, then the subsets which are possible for this array is an empty array, an array with element 5, an array with element 1, 6, then 5 comma 1, 5 comma 6, 1 comma 6 and 5 comma 1 comma 6. So these are all the subsets which are possible for your given array, and for each of the subset you need to find its XOR total. XOR total means you need to take the bitwise XOR of all these elements, and that is going to be your XOR total for that particular array or that particular subset. So if your input is 5, 1, 6, you find all the subsets, find their XOR totals, and when you will sum them all, then this is going to be equal to your output. And that is the question all about. You need to find the sum of all subset XOR totals. Okay, so first we need to find all the subset, then we need to find their XOR totals, and then we need to sum them to get the output. Let us take the example of 5, 1, 6. We found out all the subsets, and if the subset is an empty array, the XOR total is going to be 0. If it is a single element 5, 1 and 6, that is going to be your XOR total. But what if there are two elements? So if it is 5 and if it is 1, in that case 5 XOR 1, this is equal to 4. Now how does this 5 XOR 1 is equal to 4? Let me explain you. You can represent 5 in bits as 1, 0, 1. You can represent 1 as 0, 0, 1. The logic behind XOR is you need to do it bit by bit, and for each bit the output is going to be 1 only if there are odd number of ones. So right now we have even number of ones. We have two ones, right? So in that case the output is not going to be 1, it is going to be 0. For this bit it is 0. What about this bit? Are we having odd number of ones? No, we have 0 ones. So again this will be 0. And what about this bit? We are having odd number of ones because the number of 1 here is 1, which is odd. So this is going to be 1. And 1, 0, 0 is the binary representation of 4. So 5 XOR 1 is going to be 4. 5 XOR 6 is going to be 3. Again, let me show you. 5 is 1, 0, 1. 6 is 1, 1, 0. Alright. This bit will be set to 1 because we have total number of ones as 1, which is odd. This bit will be set to 1 again because we have 1 ones. This will be set to 0 because we have two number of ones, which is even, right? So 0, 1, 1 is equal to 3. Similarly, 1 and 6 will be 7. 5, 1, 6 is going to be 2. Let me show you this as well. 5 is going to be 1, 0, 1. 1 is going to be 0, 0, 1. And 6 is going to be 1, 1, 0. In this case, it is going to be 0 because we have two ones, right? Which is even number of ones. This is going to be 1 because in this case we just have 1, 1, right? And this, in this case, it is going to be 0 because we have even number of ones. So after performing bitwise XOR, the output is 0, 1, 0, which is 2. Now you can take the sum of all these elements and you will find it is equal to 28, which is your actual output for this particular scenario or this particular input. To solve this particular problem, we are going to follow two approaches. First one is recursion plus DFS, and the time complexity of this is 2 is to power n, and the space complexity is going to be O of n. We have another approach, bitwise maths, or you can say what's the maths, what's the logic behind bitwise operations. And if we apply this operation, we are going to solve this in O of n time complexity and O of 1 space, which is really good, right? But honestly, coding this is very easy, but understanding this is very hard as compared to coding this is very hard as compared to understanding this. So we can understand this, but coding it is going to be hard, and coding this is going to be easy, but understanding this is going to be a little bit hard. But I will try to explain you in the best way possible so that for you coding and understanding of both of these methods will be very easy. So let us first focus on recursion plus DFS. Why is it 2 is to power n? This is very important to know because for any given array, the number of subsets are 2 is to power n. N is number of elements in the array. So 2 is to power 3 is equal to 8, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 subsets of this array, right? This is what we are going to do. We are going to perform recursion on our elements and try to create our subset. So these are our elements. These are our subsets. We need to perform this operation to reach to this state from this particular given element. How can you do it? See, for any array, we know that an empty element or an empty array is always a subset, right? So we are going to start from this empty array. Okay. So once we start from this empty array, we have found this empty array, right? So I'm marking it as green. Now you need to process each of the element once. Okay. And at each processing, you need to take two steps. You can either include this element or you can exclude this or you can skip it. So you have an array which is empty. So you can include the next element 5 or you can skip the next element 5. Okay. So if you include it, it is going to be an array which is having one element which is 5. But if you exclude it or if you skip it, this is going to be the same array, right? Now every time you include something, you are going to create a new subset, right? This is something which is easy to understand, that if you are including something, you are getting a new data. So right now you included 5, right, the first element, and that's why you got this array which is having one element, that is 5. So we got another element of our subset which is 5. But when you didn't include anything, that is when you skipped 5, then in that case you are not gaining or you are not getting any extra information or any new information. So if you exclude it or skip it, you are not getting any new subset. So after processing 5, we got 1 and 2, two subsets, right? Now let us do the same thing with the next element 1, and this time we are going to perform the operation on both of these subsets, because right now we have two subsets. We are either going to include 1 in this array 5, so when we include it we get 5 comma 1, and we get another subset, right? This is 5 comma 1 which we have covered now. But if we skip adding 1 to this, we are not getting any extra information. This is another subset which is 5, which we have already found. What about this one? If we include 1, we are going to get a new subset. Yes, we got a new subset, right? This is our subset which is having one element, that is 1. But if you exclude it, if you skip it, you are not getting any extra information. All right, so we can skip it. And now we have 4 subsets, right? And this is our subset 3. We are going to do the same operation with all these 4 subsets. That is, we are going to take the next element which is 6. We are either going to include it or we are going to skip it. So with the first element 5 comma 1, if you include 6, you are getting 5 comma 1 comma 6, which is another subset you have got, because we are including an element. But if we skip it, that is we skip adding 6 to it, we are getting it as 5 comma 1, which is something we have already covered. With this 5, if you include 6, you are getting 5 comma 6, which is a new information. So we got another subset. And when we talk about this 5, that is when we skip adding 6, we are not getting anything extra, right? So no extra information. This is something we have already seen. And also with this 1, if we include 6, we are getting 1 comma 6, right? So 1 comma 6 is something we have covered. But if we exclude adding 6 to this, we are not getting any extra information. This is a single array 1, and this is something we have already seen. Similarly for this array, if we include 6, we are getting another subset which is having one element 6. And let me add it here. So we have another subset which is 6. We are getting this new subset, right? So let me mark it. And when we skip adding 6 to this, we are not getting any extra information. And now we have covered all our elements, right? 5, 1 and 6. And we have got all our subsets as well. Now the very important thing to understand is you don't actually need these subsets, but you need the XOR totals of all these subsets. So every time we are getting a new element, we are not actually going to store this element. Instead of that, we are going to store the XOR of these elements. For example, the XOR of this is going to be 0. So when we add 5 to it, we are going to say 0 XOR 5, which is equal to 5. So the XOR of this is 5. When we add 1 to it, we are going to say 5 XOR 1, and this is equal to 4. So instead of 5 comma 1, we are actually going to store 4 here, right? And after performing all the operations for each of the subsets, we will have the XOR total of all these subsets, and then we are going to take the sum of all of these, and this is going to be our output. So I am back on my code editor. What we need to do is we need to create a function DFS. This is going to perform the recursion. And first of all, we need to have our index. Index is IDX and our current XOR. Then if the IDX is equal to the length of our numbers, that is we are out of the array, then we have covered all the elements in our array. In that case, we can directly return the value of XOR. But if we are not at the last index, then we have some elements to choose from. So we can either take that element or we can skip that element. Okay. So if we take it, so this will be equal to DFS, and inside this we need to pass the next index IDX plus 1, and we need to take the XOR. If we are taking it, we are going to take the XOR. So our current XOR sum is this XOR. We can take the XOR of this with the current element. So XOR nums of IDX, right? So this is something we are going to do when we are including our element. But when we are skipping it, so this will be equal to DFS with the next element IDX plus 1. But we are not going to add this XOR into it. We are just going to pass the same existing XOR here. And ultimately we are going to return the sum of take and skip both. Okay. So this is going to be the total of all the XOR elements. We just need to start from the beginning. And we can say return DFS of 0, that is index number 0, and my current sum is going to be 0. So this is your complete code, recursion with DFS. And when you will submit the code, you will find that this is accepting all your test cases. Yes, we can see that the runtime is good, the memory is good. So yes, the solution is pretty good. And honestly, let me tell you that this is actually a best solution for this case because the constraints are small. And coming to the next approach, which is using some bitwise operation, bitwise maths, honestly, this is something which is really hard to understand. So let me try to explain you that approach. For that, let me jump back to my drawing pad and try to explain you this second solution, which is bitwise maths. Now this is going to be very efficient. O of n and O of 1 space. We are not going to use any extra space and just a single loop will do it. But what is the logic behind this? That's very important to know. So right now what you see on the screen is these are your subsets of your given element 5, 1, 6. Now we are not going to calculate the subsets, and the reason is if we calculate the subset, this is again going to take O of 2 is to power n complexity. What we are going to do is we are going to take the advantage of bitwise operation and its properties. So for example, if these are your subsets, the output is 28, right? You are getting the output as 28. But there is another pattern which you can follow to get the output as 28, or whatever is your given input, you can get the output based on your input. The pattern is going to be same. Instead of XOR, right? If you do the OR operation, so the bitwise OR of all these bits are going to be 1 because we have at least one 1 in all of these bits, right? We have 1 here, we have 1 here, and we have 1 here. So it is going to be 1, 1 and 1. And this is equal to 7, right? Let me put it into a formula and I will tell you how this formula is derived. It is 2 is to power n minus 1. 2 is to power n minus 1. N is 3. So it is 2 is to power 2 multiplied by 7. Why 7? Because this is equal to 7. So when you multiply 7 with 2 is to power 2, this is going to be 28, which is your output. But how are we coming to this conclusion that this formula is correct? See, in XOR, what we do is if we have even number of ones, it is equal to be 0. But if we have odd number of ones, it is equal to be 1, right? So every time we are having a 1 in our bit, in our OR bit, okay? So we are sure that we are going to get a 1 at this bit by sum of the element, right? Now how many times are going to get this 1 here? We are going to get this 1 when we do the XOR 4 number of times, or 2 is to power n minus 1 number of times. This is because if you take all of these subsets, let us take the subset with element 5. So it is 5, 5 and 1, 5 and 6, and 5, 1 and 6. And since we know that this 5 is contributing to this last bit and saying that this last bit is going to be 1. Okay, so this will be 1 in the last bit according to 5. This is not going to be 1 because we have another element 1 which is also saying that you will have last bit set as 1. So 2 elements as 1 in the last bit is going to cancel out because even number of ones is going to be 0. So this will contribute to 1. This is not contributing to the last bit as 1. This is again going to contribute to the last bit as 1, and this is again not going to contribute to the last bit as 1. So we have got 2 elements, right? And what about the other subsets we have which doesn't include 5? So we have 1, we have 6, and we have 1, 6. And try to find the same thing again for the last bit. And the operation is going to be same for all the bits. Okay. So this 1 is going to say, okay, the last bit is going to be 1. The element 6 is going to say the last bit is not going to be 1. So this will say the last bit is 1. This will say the last bit is not 1. And the combination of 1 and 6, this is going to say the last bit is going to be 1. And the reason is 1 will say it is 1, 6 will say it is not 1. But we have odd number of ones. So the last bit is going to be set as 1. So how many ones did you got for the last bit? So we have got total 4 number of times from these subsets that the last bit is going to be set as 1. And when you do the operation for all the bits, when you try to find the operation for all the bits, you will see that we are getting it 4 number of times. And 4 is equal to the half of all your subsets, okay? And we have total number of subsets as 2 is to power n. And when you do the half of it, this is going to be equal to 2 is to power n minus 1. And that is why what we are doing is we are using this formula 2 is to power n minus 1 multiplied by the sum. Okay. So this is the complete code of this particular approach. We are having an initial number all sum as 0. We take the bitwise OR with all sum for each of the element in the array. And in the end, what we are going to do is all sum will be multiplied by 2 is to power n minus 1. Right. So we are going to take power function 2 here. And then this is n minus 1. And this is your complete code. When you will submit it, this code is going to get accepted. And this code will be very fast and will be very efficient as well. Because you can see 100% time complexity, and memory wise also it is good. So guys, that's all about this particular problem, and that is all for this video as well. So I hope that you understood both of these approach, that is finding the subsets and without finding the subset and using the bitwise maths trick. So if you did understood about it, and if this video did help you, then make sure that you hit that like button for this video. And if you're not subscribed to my channel as of now, then make sure that you subscribe to my channel as well. And I will see you guys in the next video. Thank you for watching this video, guys.